Let me work out an example of volumes of revolution. So say that we want to find the volume obtained by rotating the region between y equals e to the x, y equals 1, x equals 0, and x equals 3 around the line y equals 1. So in this case, notice that we are rotating this not around the x-axis or the y-axis, but actually around a different line. So that is going to be one of the main differences that we're going to have. So let me start by sketching this region. So what we have is that we have the first curve, which is e to the x. Then we have the line y equals 1. And then we have the two vertical lines, x equals 0, and then x equals 3. In other words, the region that we're trying to rotate is going to be the region enclosed by these four things. So it's going to be this part right here. Looks like a little wedge. Now notice that we're trying to rotate this thing around y equals 1. In other words, the axis of rotation is this one right here. This will create a shape that is going to look a little bit like this. So it looks pretty much like a trumpet. So all I'm going to do is I'll try to describe what the cross sections look like, find the area of the cross sections, and then write down the volume for this. So again, for reference, what I'll have in here is that the area obtained when rotating this part is going to look like this little trumpet. So when I look at one of the cross sections, the cross sections are going to be these discs that we're going to find over here. So the most important part is that the radius of these discs, the radii for this, is actually going to be the line between the two functions e to the x and y equals 1. That difference is going to give me what's the radius. So what I'm saying over here is that the radius of this cross section, let me call it r, this is going to be the same thing as the difference between the top function, which is e to the x, minus the bottom function, which is y equals 1. Notice that e to the x is the region between the x-axis. So this whole thing is e to the x. And then 1 is going to be the distance between the axis and the line. So this is 1. And you can see that r, the radius, is going to be the difference between these two. So in the end, what I would have is that the volume for each of these cross sections, each of these discs, is going to be nothing else but area equals pi r squared. So again, r in our case is going to be e to the x minus 1, which gives me that the area of these discs in terms of x is going to be pi e to the x minus 1 squared. So I can simplify this, and I have pi e to the 2x minus 2 e to the x plus 1. Then I just have to put all these areas together, and that will give me the volume. So in order to come up with the expression, it's always going to be the integral of the cross sections dx. In this case, we have that these cross sections are perpendicular to the x-axis. So I just have to identify the limits of integration, and in this case, I think it's going to be clear to see that it's from x equals 0 to x equals 3. So we have integral between 0 and 3 of pi e to the 2x minus 2 e to the x plus 1 dx. And now it's just a matter of working out this expression. So I can write down the pi in front of everything. Then I have the antiderivative of e to the 2x is itself divided by 2 minus 2 times e to the x, which is the same, plus x, everything between 0 and 3. And now it's a matter of plugging the numbers. So this should be pi. Then we would have everything at 3, which is going to be e to the 6 divided by 2 minus 2 times e to the 3 plus 3. And everything at 0, which that would give me 1/2, which is e to the 0, minus 2. Again, e to the 0 is 1, plus 0. So I can simplify this finally, and I would have pi times 1/2 e to the 6 minus 2e to the 3. And then I would get 3 plus 2, that will give me 5, minus 1/2, that will give me 4.5, which is the same thing as positive 9/2. And that will give me the volume of the original region that I had over there.